All right, so thanks for giving me the opportunity to speak here. As the introduction said, I'm part of the Industrial AI Research Center at UniSA. And in a nutshell, our expertise includes artificial intelligence in the broadest sense, including machine learning, knowledge representation, expert systems, mathematics, computer science, and engineering. And so we work a lot in applied AI. So our research is usually driven by applications. We do digital twins, industry 4.0 type research, optimization, modeling, and interoperability of systems. So a large part of our work is in bringing together the data, as we just heard, which is a big job before AI can actually be applied. And so today I'd like to talk about how artificial intelligence techniques and digital twins relate to each other and how each can enhance the other. All right. So let's see. Green means go, I guess. Okay. So what is a digital twin? So a digital twin basically is a model of something. Usually model includes the structure and the behavior and the associated data of usually a physical system, but it can also be something else like a process or a service that is being modeled. And so the purpose of that model is to understand the past and present operations, make predictions, and ultimately support decision-making in some form. And so usually digital twins are used as simulations. So digital twins allow cost-effective simulation without having to have the hardware in place and without having to disturb the live operations. So we can simulate certain processes or certain activities or ascertain the effect of certain decisions just by looking at that digital model. And so to do that, we need a good model. Unfortunately, for most situations, models are hard to construct from first principles. So for most complex systems, we need some kind of data-driven approach to construct a digital twin. And so a lot of approaches use a combination of machine learning and partial explicit manual modeling to construct that particular digital twin. And so as a result, hopefully we get a powerful digital object that can be used to optimize the physical world and improve operational performance. So Gartner estimated that about half of the large industrial companies will use digital twins by about 2021 or 2022, and we can expect about 10% of operational improvement from using digital twins if they are used effectively. And so what's in a digital twin? And so a digital twin design is made by gathering data and creating a model that represents the underlying object. So we can test that model and determine how accurate it might be. So that includes essentially data collection from sensors that might sit on physical devices. That includes data acquisition pipelines that take that sensor data collected in, let's say, historians and process it. It also includes engineering models that model perhaps the processes or first principles that underlie the physical processes in our plants. On the other hand, we have the digital world, where we have software that takes the data, presents it for monitoring purposes. We have big data pipelines that help us store and process the data. And we have AI and machine learning that tries to aggregate the data and make sense of that data. And so as such, a digital twin is a bridge between the physical and the digital world. And so as I mentioned earlier, digital twins can be constructed in a number of ways, from first principles if the components or the things we are modeling are simple enough. They can be learned from data if you have enough data, or usually what we do is we create hybrid models to compensate for the fact that we don't have enough data or some phenomenon hard to model just by looking at the data. All right, so assuming we've successfully constructed such a digital twin, what can we do with it? Well, we can use it for design and planning. We can do what-if analysis. We can simulate the effect of certain decisions and see what impact they might have on our operations. We can use them to understand what the current situation is in our physical object, in our plant. We can use that for monitoring. If something goes wrong, we can use it for root cause analysis, or we can use it for prognostics to avoid problems in the first place and do perhaps a condition-based monitoring and condition-based maintenance, not condition-based monitoring, to avoid problems in the first place. And we can use it to optimize the way we operate. And so the underlying technologies that enable that include AI and machine learning. So essentially, the AI part of a digital twin creates a simulation model that can update alongside of the physical, the concrete process in our plant. And we can use that model as an assessment entirely in a computerized world. We don't necessarily need to go into the plant and test what the impact of certain decisions are. And so we can do that along the life cycle of our plant, from design to commissioning operation, even to decommissioning and deconstruction. Yes, therefore, digital twins are the key to Industry 4.0. They provide automation where possible. They are the framework for data exchange, where we collect all the data that is being sensed. They're key to having intertwined, joined up manufacturing processes that span more than one component or more than one sub-process in our organization. And ultimately, they help us de-risk our product rollout because we can simulate what's going to happen on the digital model. And so how does AI fit in all of this? And so there are three ways AI and digital twins can benefit from each other. So the most common way is where the digital twin makes use of some AI to analyze the data. So that's what I've got here on the slide. We use AI on the one hand to construct part of the digital twin, where we take the sensor data and some model of our physical object. We apply machine learning to it to construct partial models of some of the components. We test them to see whether they accurately model our physical system. If they pass validation, then we have a digital twin. That digital twin can then continue to ingest data from the physical object. AI algorithms can make sense of that data to identify trends, outliers, predictions, and so on, and that way help decision support. In this context, AI can also accelerate the design process by essentially providing a simulation environment where designers can quickly ascertain which designs might actually be better or worse than others. And so digital twins help us to plan for changes before we actually need to enact them in the physical world. So another way digital twins and AI relate to each other is that digital twins can be used to enhance AI. So the previous speaker mentioned that in some cases we might not have enough data. And that's exactly where this scenario plays in. In lots of applications, we may not have enough specific data to train an advanced neural network, for example. And so a popular approach to solve that problem is to just generate some data. So if we have a good enough digital twin, if we have a good enough simulation that models relevant aspects of our physical systems, we can use that digital twin to generate data, which we can then use to train a deep neural network to then solve some problem that we're interested in solving. And in fact, there's colleagues of mine at UniSA are doing exactly that. They are essentially trying to predict life signs such as breath rate and heart rate for animals remotely based on computer vision camera videos, basically. And so because there isn't a lot of training data to do that, they developed the virtual rabbit in a game engine which simulates the breathing, generates computer vision data, and then they train a deep neural network to essentially extract the heart rate and the breath rate from that artificial data. And it works surprisingly well. If you then take that resulting model, apply it to real video data on real animals, gives a very good results in that regard. And so the third interaction between AI and digital twins is the way the information is presented if we have humans in the loop. And so if we interact with a digital twin, yes, we can do it in a traditional way by looking at a screen and see some numbers on there. But increasingly, there are opportunities to use it to interact in different ways. For example, using voice commands, using augmented reality and gesture interactions, where we can directly see and almost feel the data overlaid on visual images of the physical object. We can use AI gesture recognition techniques to directly interact with these artifacts. And we can use AI to infer what information should be presented to the human so that they can make effective decision making. Right, so we've covered the three main ways AI and digital twins can interact. And so now I'd like to give a few examples of the digital twin work that we are doing at IAI and our research partners at UniSA. And so I'll start out with perhaps a somewhat classical example. We have a Industry 4 test lab at the Future Industry Institute, where they develop technology to develop nano-scale surface coatings. Things like something you might have in your glasses or sunglasses, anti-reflective coatings. Except they're interested in developing coatings that not only have optical properties, but that also repel heat. So we can put them, for example, on car windows so that your car doesn't heat up in the sun. And so they've got this plant there. We've developed a digital twin in terms of the visual appearance, all the components that make up the machine, the CAD models, and we can visualize that. We've also added software to collect all the sensor data that comes off that machine. So we have a comprehensive history of all the runs that go through that machine. We've complemented that with software to collect the test results of the resulting products that come out of this process. And we are working towards essentially using that to then use AI to design the experiments better. So to use AI for experiment design to see what kind of parameters, what kind of materials, what kind of layers should be trialed in the subsequent experiments so that we don't need to waste a lot of runs to figure that out. And so AI here is used to monitor essentially trends and outliers that happen in the production. Eventually, we are seeking to also control that plant, but at the moment, that's a traditional PLC that controls this. We are aiming to develop AI techniques that predict the qualities of these coatings and ultimately also help explain why certain coatings are more successful than others. Next is a quite different example. So I was trying here to collect examples that kind of show the breadth of what digital twins can be used for. So the classic example with the machinery is quite well known and fairly popular. Here, that next example is a bit different in that it's from agriculture. So we're working with a sensor company that developed sensors for measuring irrigation and plant stress in fields and farms. And so they are capable of developing essentially what's a digital twin of the field. They can know how stressed the plants are, how much water they've taken, what the growth rates are, and all sorts of agronomy statistics that you can calculate. And so our research aims to complement that with other information, for example, financial aspects, human resource aspects, so that we can come up with a more comprehensive digital twin of not just the plants in the field, but the entire farm. And so we bring together financial information, human work-related information, how many hours would need to be spent on certain tasks, infrastructure and environmental costs, for example, water costs, electricity costs. So these vary quite a lot for farmers. And so the decisions on whether to pump more water onto the field is largely affected by what the electricity and the water price is going to be, what the weather forecast is going to be, and what impact that might have on the plants. Should we irrigate today, or should we wait a day? Should we wait 2 days? What happens if we spend more money versus less money in terms of the plant stress and ultimately the growth outcomes? So here we use essentially machine learning models and some rule-based systems to assess what is the current situation and whether plants are about to enter some area of stress. So for example, on the next slide. So there's a dashboard that looks something like this, where various factors of the plants are monitored by the sensors. And we can see that on the bottom chart, we can see that there's this black line here. We can see that at some point, plants are about to enter that red area, where that indicates that there might be water stress in that plant. And so now the question is, if you can see the trend coming, say, well, tomorrow that plant's going to be stressed, what should we do? Should we irrigate today or should we wait? And so the system will then take that information along with weather forecasts, power price forecasts, and give advice to the farmers and say, well, what happens if you irrigate today? Is it a good time to irrigate now or should we wait? And that has, except for the, in addition to these power-related, cost-related factors, things like wind speed and other factors also need to be taken into consideration. So it's a quite different digital twin. We do, in the interest of time, maybe I'll skip over some other examples. We do similar things in healthcare, where we look at patient journeys through various healthcare providers to identify what are anomalies. So this is kind of process-related digital twin, not technical at all, where we use process mining technologies to find out what are the common processes that certain patients go through, what are their treatment outcomes, and what are the outliers. We do a lot of work in defense. So this project with BAE Maritime and Innovative Manufacturing, CRC, where we are looking at novel visualization analytics methods to increase awareness and optimize the operations on the shipyard. And so there's a group, colleagues of mine working on the visualization aspect of this, how to present information about effects, about operations, and we are working on the data-driven analytics that help identify where the bottlenecks might be on the shipyard and predict the impact of certain unforeseen events like failures, non-conformances, or simply staff arriving without anybody having planned for the next truck turning up today. So to do that, the effort is actually quite large in bringing all that data together. So in order to pull that off, we need to integrate logistics information, sensor information, scheduling and work planning information, material handling, permits, and safety information that might constrain what can be done at what period of time. And so as we saw before, again, the analytics part in that is comparatively small relative to the work that is required to bring all that data together. And so what are the challenges in producing digital twins that can do such decision support systems? Data is often a challenge. Data is often not available. It's in siloed information systems that need to be opened up and data needs to be extracted. Data quality is an issue, especially if there are people involved. In healthcare, for example, data is often very incomplete, very, well, let's say, poor quality. And perhaps some of the events that we wish to predict are not all that well represented in the data, especially if they have adverse outcomes. So all of these are challenges that need to be taken into account before embarking on constructing such a digital twin. We also have issues, well, there are issues with continuous adaptation, where the digital twin needs to be kept in sync with the actual physical object. And so although there are reinforcement learning and control technologies that can help there, it's still that there's quite some effort in making that work correctly. Maybe apart from cost, one of the biggest challenges that remains is to build large-scale digital twins. So technologies to build a digital twin for one physical component is quite well developed. But to take, let's say, digital twins for 10 different components and put them together in one digital twin for a whole plant, that's a completely different story. So we have interoperability issues between the models, which may have incompatible assumptions, and we have interoperability issues between the various platforms that you can buy commercially that are all suffering from vendor lock-in to some extent. And so there are some challenges to overcome here. And indeed, we are starting a project in that area with the Future Energy Exploration CRC just as we speak. In interest of time, I think I'll let you read the slide and instead take a question. Thanks for your attention.
Thank you so much, Dr. Wolfgang. We have time for one question. Sorry.
Thank you. I'm just really interested to find out if you see any bias arising from the use of digital twins, and if so, what types?
Right. Yeah, I think there's potential for bias. In the research project that I was involved in, we have not dealt with that issue, but potentially a model is always a simplification of some real phenomenon. And so depending on what's omitted in that simplification and what algorithms you apply to it, there's a potential aspect of bias there. And so you have to be very careful that you don't accidentally omit significant data or a significant component of your model that would then suffer from a bias. And so there are machine learning techniques that try to counter that and try to detect if there's any bias. There's also models that are perhaps resting on the principles of causality, which are a little bit more robust sometimes, but they're all still in fairly theoretical approaches. I haven't seen any commercial grade software or anything like that that would address that very well. Yeah, sorry, I don't have a clear answer to that. Right. Then thank you for your attention.